Ich bin auch neugierig. Muss mega lustig sein. Okay, everyone. Hello. Hello, my name is Frank. Welcome to Digital Design and Computer Architecture. This is a great moment for me. I've never had 554 students visit a class that I'm giving. I'm so happy that you chose to be here. Right? Right? You're not being forced to come here, right? Absolutely not. Okay, this is great. This is great. I mean, I thought it was mandatory. I said, no, they like my lecture. Okay, so let's be honest. I'm from electrical engineering. Who's here from electrical engineering? Ha! Oh, hello. You're lost. Okay. So you are here because you're in computer science, and I'm from electrical engineering. Normally, these are like the big enemies, right? I'm afraid of you. There's 300 of you against me. And I have to convince you that it is worth your time being in this lecture, listening to me, doing the exercises, and I will try to do so. However, it is clear for me that if you really wanted to study electrical engineering, the building was just there. You could have gone there anytime you wanted. So I am aware that you don't really want to be electrical engineers. Who wants to be electrical engineers? Dude, it's just there. Just enroll to the other class. Anyway, what we will try to do, I mean, I'll go into the motivation and the other things as well, is we understand that this is not for electrical engineers. We are trying to give you the perspective of what will try to help you in your career as a computer scientist, so that you can get a little bit of information what we are, what those people, those geeks at electrical engineering end up slaving through, I don't know, 4 or 5 years of their education. So we are trying to put the highlights to you so that you can keep up talking with them, and you know, they don't be bullied by those people, but you know, we are trying to keep it interesting enough to keep you engaged. It's difficult to have 300 people not walk out of here. I'll do my best. So first things first, how to follow the lecture. The lectures are here in ETH Hauptgebäude F7. I'm saying this because there's a bunch of recordings and other things going on. I mean, I'm super happy to see so many people here. I know a couple of them are over in F5. There's still some places here. Usually, some people tend to not visit so much, so maybe we can keep everybody here. There's a live stream of the lecture on YouTube. First time I'm a YouTuber, okay? And recorded lectures will be available on the class website. I'm looking very much forward to that. Okay, also on the class site, you will have all the presentations we use and all the information from previous incarnations of the lecture, including slides, videos, exams, and we have a Moodle page for discussion. So there's a lot of opportunity for you to interact. So, you know, you don't have any excuse. So, motivation. Computers are everywhere, right? Who still has a computer that looks like this? Okay. Old school, okay. But computers actually take also different forms. A lot of us are aware of things going on in the cloud, big data centers. There are things that fly around, are everywhere, or are small, attached to your cell phone. So we have actually computing things everywhere. And as a CS student, you will live and breathe computers. You will not necessarily be designing them themselves, the box, but computers will be an essential part of what you are endeavoring in your career. So what we will try to do is what goes into them, what's into the computers, how are they built, and what is easy for us to do, like us, the general technical people, electrical engineers, whatever, and what trade-offs do we make? That may help you understand the tools that you are using a little bit better and be able to communicate better with people who are designing computers. So the purpose is what's under the hood of a computer, learn principles of a digital design. Now comes the bad part. Learn to systematically debug increasingly complex systems. Okay, and the cool thing is, I mean, I've been involved in this lecture for more than 12 years. In the end, we want you to be able to understand how a microprocessor is designed and built, and we will help you a little bit so that in the exercises, you will end up building parts or a larger part of a microprocessor. And if you want, the next time you go to MediaMarkt and somebody is trying to explain you how great a processor is, or you go to EE or Intel and say something like three-way superscalar pipeline, blah, blah, retire, 3 instructions, 12-stage super pipeline, that kind of thing, you will say, okay, I know what that means. Okay? So the lecture is about computers, what's inside, and so not only that, we will go in, that is the motherboard, has a bunch of bigger chips, digital designs, and we want to also go down inside the processors and how learn how we can build them. Now, this lecture is brought to you by Onur Mutlu Safari Research Group. They are experts in computer architecture, hardware, software systems, bioinformatics, security, memory. Members of the Safari team, they are very shy. They are hiding there in the corner. And it's called Onur Mutlu Safari Research Group. That is Onur. And Professor Onur Mutlu is one of the most distinguished people in computer architecture. He's worldwide very well known. He has had a remarkable career and currently is a full professor at ETH Zürich. His lectures are very popular, so we are just, riding on his coattails. Currently, he's at a sabbatical leave in the US. For those of you who don't know, if you're involved in an academic institution, every now and then you are granted a leave. You can go and visit another place to broaden your horizons, get some new impulses and inputs. So this is a semester he was away. And this is not Professor Mutlu, that would be me. For those of you who can speak Turkish, my name is Frankan Gürkaynak. Everybody calls me Frank. I'm not a professor in case you are trying to write an email to me. I'm just a senior scientist. Senior means old. I work in the group of Luca Benini. I'm my bachelor master in Istanbul. I did a PhD here back in the day at ETH Zurich. And I also run the Microelectronics Design Center. I'm involved in a number of in a number of lectures. These ones I have in both VLSI 1 and VLSI 2, where we teach how to design digital circuits a little bit more. Those are actually electives for computer science if you didn't have enough of me after this thing, and there are a couple of other ones. I'm not the only one who is presenting. I have also, Mohammad, say something.
Hello, everyone. I'm Mohammad, a senior researcher and lecturer working with Professor Mutlu. I did my bachelor, master, and PhD all in Sharif University of Technology in Iran. And I joined ETH Zurich as a postdoc since 2021. I've been in this course for 2 years as the head TA, and this semester I have the pleasure to be one of the instructors. Nice to meet you all.
Okay. You didn't clap for me that much. So changes this year. So these are the things that didn't change. The exercises are identical from last year. First of all, no judgment. Anybody repeating from last year? Okay, a few people. Good. The teaching goals of the lecture remains exactly the same. The recommended textbook is exactly the same. Do you feel a but coming? Okay, there's a but. But I cannot keep the same speed as Professor Mutlu. Okay, I can keep it up for one lecture maybe, but not for the entire series. So I have a bit of a slower style. This means that I have less time for some of the more advanced topics. So this year, the exam this summer and also the follow-up exam will be made according to what we are able to cover. It will be slightly condensed because I'm not as good. And don't worry, Professor Mutlu will be back for the next semester and we will pick it up. I hope that's okay. There are the few people, they're already saying, hey, Professor Mutlu had already covered. Okay, so a few words on what I do. I work on open source, energy efficient ICs. These are the type of things we do. So if you take a look at it, we are pretty proud of this. We call this guy Okami. Does anybody know what Okami is? Harry Potter? Okay. Anyway, so that piece of shiny thing there is a chip that contains 216 processors. There's 2 of them. And then there's a bit of memory, and everything here is open source available. There is more than 1 billion transistors that make up the system. So it is a fairly complex system. So the question comes, how do we manage systems that have a lot of complexity? And the answer to that is actually 3 things. We use abstractions, we use what we call a discipline, and the 3 Ys, hierarchy, modularity, and regularity. If you take a more commercial example, the Apple M2, which is in a number of laptops and computers, this is a picture of it. It's actually quite a small thing. So this is 1.35 centimeters on one side, approximately. And the interesting number, I mean, this looks all great. Here is the number. It says transistors. We don't yet know what they are, but there's 20 billion of them. 3 for every person who's alive today. I mean, that's ridiculous, and you can put it in a laptop. And somebody has to design and build it. And when you look at it, you will already see, I mean, this is an abstraction, but you already see that there are some blocks that are identical, Control-C, Control-V, right? Copy, paste. Somehow things have been made there. Without this, we are not able to manage complexity. So abstraction is what we call hiding details when they are not important. And the abstraction levels, I mean, you can define this in any different way you want, but at the very bottom, physics helps us. We are talking about electrons. Out of that, we make transistors, analog circuits, digital circuits, logic. And at the very top, there is application software. Maybe today you also have the cloud level. You know, you can argue about what the different levels are, but they help us concentrate the problems and solve things at certain levels. So this course, we are going to cover this level of abstraction. We're not going to look below. We are not going to look above. So we will talk about architecture, which is what the processor understands, the instructions, the registers, the microarchitecture, how it's implemented, pieces that make up the microarchitectures, adders, memories, and then their basic building blocks, AND gates, NOT gates, and things like that. And you will notice that I tend to lie a lot. Okay, there will be a tiny lecture tomorrow where we will actually dip a little bit here and then go back. Okay, good. Discipline. Discipline is you have a number of choices when you make your designs and you realize you'll just have a nightmare choosing. So you say, I'm going to restrict my choices to a smaller subset that I can concentrate working on. And I'll talk about that in a second. And hierarchy is what helps us the most. You also, Caesar used that, right? Divide and conquer. You have a larger system divided into smaller parts, and that smaller part is made up of other smaller parts. And then you break it down until a point that it's small enough that you can tackle it, and then you work yourself backwards. Now, modularity helps with this because it says, let's build modules that have well-defined interfaces, and so that it's easy to connect them, even though I don't know what's inside them. So this is what helps with modularity. And regularity plays into the same thing again and saying, instead of making 10 different modules that more or less do the same thing, why don't I choose things that can be built up of the same thing multiple times rather than having exceptions all over the place? So these are the things that help us reduce or tackle problems that have complexity. So this is what we are going for. Now, questions so far? Bless you. Okay, digital abstraction. Now, most physical variables that we use, like voltages, frequencies, mass, anything, have actually a very large range. The potential on a wire could be 1.35 volt, 1.317 volt, or something in between. Instead of considering all the digital, all the values, the digital abstraction is very simple. They say, let's just put all electrical signals into two categories. It's either true or it is false. It is 1 or it is 0. And then you actually have your way of representing things. So, 1 and 0 can be represented by specific voltage levels, could be rotating gears, fluid levels, whatever. And digital circuits, the ones that we will be looking at, depend on specific voltage levels to represent 1 and 0. The level itself is actually not that important. I mean, it could be 1.2 volt, 1.8 volt, 2.5 volts, 5,000 volts, okay? It doesn't really matter. The point is there are two levels. There's a high level, there's a low level. And we call them, in the end, a binary digit, and the name is a bit. Now, that doesn't sound like the most exciting thing to do, especially trying to keep you all here motivated and glued to your chairs. So the question is, can we, just if we had ones and zeros, can we write like 2024? And some of you already know the answer, and this one seems much more doable. But if you want to write something like this, and what we will try to tackle are how can we represent these values and how can we calculate with such values if we only have ones and zeros. Now, there are some embarrassing examples I'm going to show you, not the way you think it. I try to keep all the examples from the lecture book so that when you look after the lecture into the textbook, you will see the same examples. So there is going to cafeteria for lunch, and there is this like dilemma. You want to make a decision, what shall I eat for lunch? And these are your choices. I hope you have better choices. You won't eat lunch if it's not open or if they only serve cabbage. Did it resonate with you? Who says yes? Oh, come on, you're being too nice. Okay. But if you look at it, we will be able to express such problems in what we call a truth table. And eat lunch will only happen if it's open and not cabbage, kind of thing. So it was a statement that we turned into different zeros and different ones being there. And we will learn how to formulate problems in truth tables. And once we have them, we will see that we can turn them into circuits. At some point, I promise you, this is going to get interesting. Now, again, from the book, I have no idea. There is this little snail, and he's walking on a ticker tape. And if he sees the sequence 1101, the snail will smile. And your job is to make a circuit that makes this happen. I know, right? Okay. And part of the lecture, we will actually see how that type of problem formulation will turn up into a logic circuit that seems to have these funny bubbles and things. And then there is this Y, and the Y will actually correspond to this thing smiling. But this looks boring. I agree. Who thinks it's boring? Why is this part more honest than this part? Okay. We will actually, instead of making these drawings that look like something your father or grandfather was involved in, use something that we call a hardware description language to be able to express our designs or how the circuit should function in a more structural, computer-oriented way. So you will learn how to describe hardware in this secret language called Verilog. We will see how we can add, multiply binary numbers. And once we know how we can add and multiply two numbers, really at the ones and zeros level, we will be able to take these and start building processors. So this is a simple, relatively simple 32-bit processor. And you know that unit we were talking about just finds its way here, and we can start building on it. And then we can actually run programs on the processor that we have built. So this is also part of our lectures. And to tie you up to the higher levels, we will also briefly see how the higher level, the most up thing, high-level language program gets from a compiler into this thing, from an assembler, ends up being the ones and zeros we were talking about, and gets executed. So this is the path that we hope we will be able to take you through in our lecture. Now, sorry, questions? Any questions so far? From everybody tuned out, okay. Good. So, before we start with the lecture, there is a number of organizational aspects. We will try to cover them, information on the lecture, on the laboratory exercises. The second hour, Ataberk will actually present in depth what the exercises are about and how we will continue. The most important thing, the exam. Okay? Are you excited about? Yeah. Okay, let's start with the schedule. We have 2 lectures. You found the first one. The next one is exactly at the same place tomorrow. I'll see how many show up. There are no lectures on specific days. There's Easter break, and one Thursday goes away for the Ascension. The lab exercises will start in the 3rd week of the semester. You will see the schedule. The first lab session is on Tuesday, and there is another one on Wednesday. This means that you have the lecture, and then next Tuesday there's an exercise. So this is why we have to start them a little bit later to be able to cover the material that we have in the first exercise. We need a little bit of warming up. This is why it starts in the 3rd week. They will be in computer rooms in the Hauptgebäude around here. There is many of you. Fortunately, we have a large army of assistants that will help you. And we have 4 rooms, right? We have 4 rooms. We will divide you into groups, divide and conquer, right? And we will get through this. Not believing. So, for the course, we are using the book by Harris and Harris. There are actually, I will try to stick more closely to this book. Onur was going much faster, so he was bringing in much more material. I'll try to keep most of it from this main lecture. There will be some additional lectures, and that material will be provided. Now, if you're looking online, there is actually a second version of it. There are even more versions of it, newer versions. These should all be available online for members of ETA, so you don't need to buy physical books and, butcher trees and melt things. Interestingly enough, I can talk about it at length, but the older edition of the book is slightly more aligned to the lecture. Okay? It's because I'm old. There's an annoying story in between that, but the contents of the book, so they start with the story of ones and zero, chapter 1, chapter 2, 3, logic design, Verilog. We will be following this structure closely, and I'll try to keep the examples and figures aligned to the book as much as possible, not to add too much to your burden. Such a nice person. Okay, laboratory exercises. By the end of the lecture, with a little bit of help, you'll be able to design your own processor and make it work, meaning that we will be able to execute a small program running on it that should give you a pretty good idea about what goes on when people design new processors, what kind of trade-offs they make, how do things come together, and then you'll never ever have to hear about it again, unless, of course, if you really want to. Now, you will understand how processors work, get an insight, how everything comes together. And there's a flip side to it. And there are 2 flip sides to it. So the goal is a bit ambitious. We could have kept the exercises fairly, let's say, mundane. There's a number of digital circuits, classes. The exercise over the years did not change so much, but we wanted to get you to build the processor. So some of the exercises will be a little bit challenging. There is the other part is that the exercises go a bit slower. So we will be way past some of the topics in the lecture, and we will be seeing them in the exercises throughout we are spreading it out over a longer time. We will do our best to keep you informed. I'm just warning you, there is some overhead available, will be some overhead. Now, every group will be using what we call an field programmable gate array, an FPGA board. We will pair you in groups of 2, and we will give one of these guys to you, and you'll keep them. You'll work with them. You'll bring them to the exercises, run your exercises on it. As I said, there will be 4 sessions per week. There is Ataberk will explain how we can enroll in it. There's something great about it. You cannot destroy this. You can do, you can destroy it if you really set your mind into it. Don't make YouTube videos of how I destroyed the indestructible thing. It's not worth it. But you can't destroy it by programming. Yes, question? That's a good question. The question is, would electrostatic discharge destroy this thing? We haven't seen one done yet. Don't take it as a challenge. There are more worthy challenges. This is designed by Digiland. I'm not being paid by Digiland, but they make quite robust things. So those things, electrostatic discharge is part of what, let's say, electrical engineers design their circuits against. So it is possible to design circuits that are more robust, or they can work in more hostile environments. And these boards were made for classroom use, so they are a bit more robust. And as I say this, I'm sure there will be a lot of trophies and saying, I destroyed this. There is something very great. See this? There's a 7-segment display. In case any one of you want to be a James Bond villain or something like that, this is very important. Allows you to build a timer that will just expire and show the exact time the bomb will go off. Very, very cool. So Ataberk will talk through the exercise in the second hour. And if you have more questions, he's the right person to answer. Now, the part that you all love to hear about, examination. Who says grades don't matter? Yeah, grades don't matter, actually. All you have to do is get a 4, right? So, first of all, the exam is within the exam period, sometime in August. We have no choice over it. It's not like Peter comes to me and says, Frank, when do you want your exam? And I say, make it Saturday. Make it at midnight if possible. It's scheduled by ETH. We have absolutely no influence on them. And I hate Saturday exams as much as you do. So, there will be 6 to 8 questions related to the lectures and the labs. Everything we cover in lectures and labs are fair game. If you have friends that are at electrical engineering, they will tell you that if Frank wants to be mean, he will get you. So we are not trying to fail you, okay? The exam is not there to make you fail. And yeah, sorry.
Will the exam be a theory exam, or will there be a practical programming part on the field programming?
It would have been so great to have a practical part. It's just impossible with 550 people. Unfortunately, the size of it's already been a struggle to keep the practical exercises. When I was first involved in it, 2011, we had 170 students. Now, this morning there were 554. We just had to buy another 190, 75 new boards this year just to accommodate. They weren't destroyed, okay? It's just a students increase. I say this and it will get destroyed. 6 pages of handwritten notes are allowed, so you don't have to memorize everything. When we say 6 pages, the idea is actually clearly this. You basically need 1-2 pages so that you feel good about it. We don't say 1, 2, because then you will freak out and try writing like with tiny, tiny microscopic letters. That's why we say it's 6. We say there's a limit, 6, so you don't go and say, oh my God, I wrote only 2 pages, but I could write 20. My God, my God, my God. So this is the entire philosophy between coming to 6 pages, okay? Should be doable. We will talk about that later. There's 100 points of the final grade, and 70 of it will come from the exam. 30 of it you will collect happily by attending the exercises. So this is an incentive for you to follow the exercises, be in all exercises, make sure to hand in a small report, check the checkpoints, you'll collect the 30 points, you'll be already ahead against people who decided not to show in the exercises. Previous exams are available on the already on the class site. As I said, I'm a bit slower. You already noticed I'm just dragging on, trying to make stupid jokes. And so last year's exam and this year's exam will be slightly different. Don't worry, we also have exams from the time where I was involved, and we will also make those available. Yeah, this, by the way, is the Safari ETH.ch, DDCA is the class web page. I stole this slide from Professor Mutlu because I really like what he explained. We will enable you to learn and prepare you for the exam. So during the class, don't think about the exam. Focus on learning. We have things to prepare you for the exam. Reinforce your problem-solving skills. Do not worry about the exam while listening to the lectures. Traditionally, most of you pass this class. I know some of you won't. That's life. I think all of you are great. Doesn't matter what grade you get. But our guiding principle is you are in a block of different classes, right? We don't want to be the reason why you pass or fail the block. Okay, so this is actually, we want to give you additional information. We don't want you to be, us to be the reason why you're not passing your block exam. Yes, question? So I'll repeat the question because it's not being captured, and anyone from the EE department will laugh at me when I say this. You are allowed to write handwritten notes on a tablet and print it out. If you were in electrical engineering, I would say over my dead body, but here you have this freedom. Yeah. At some point, I can show you all the feedback I get for not allowing it. It's brutal. I had therapy for it. So basically, we will release a lot of material for you to prepare for the exam. Yeah, so if you need any help, the preferred way is to write to Digitaltechnik, at least in ETH.ch. All lecturers and assistants will receive this email. This is great because you will reach out to everyone. And if one of us is busy or not responding, chances are very good that someone else will respond. Now, for a couple of years, Moodle allows anonymous posting, which is great. You know, you don't want to be maybe associated with a, you know, you will think that we will think badly of you or something like that. You can post anonymously. People can answer, students can answer, assistants can answer, we can answer. So this is not used as much, unfortunately, but you know, I think it's a great tool, allows everybody to communicate. You can also write directly to me, for example, just put DDCA in the subject. I get more than 100 mails a day, so that I can tell apart. It's actually better to write to the mailing list so that more people get it and can reply, because any one of us may be a little bit encumbered and not answer immediately. Yes. Wow, I'm fast. Further information is our lecture webpage. Out of historical reasons, we still have the Digitaltechnik one, but the new name of the lecture is DDCA. And now would be a great time for you to ask some questions. Yes?
being physically at the lab required?
You have to be physically at the lab. It's a nice, they are nice rooms. But yeah, I mean, there are exercises. It's best to work in groups. The main problem is, I'll get to that question in a second. The main problem is the FPGA boards need some software that's installed on the computers. The software here, we know the licenses, the software, the versions, the board, the connections, and these things work. It is sometimes hard to replicate it at home. I'm not saying it's not possible, but if everybody tries to do that, some of you will be more advanced, I mean, have an advantage over the others, and we will be trying to solve, I'm using my favorite operating systems, favorite patch, favorite thing, it doesn't work, your lecture sucks. Sorry, there was one from that. Yeah.
What if we miss 1 week? Can we miss like 1 week, or do we have to be at every lab?
I think Ataberk has a.
Yeah, it's fine. You can miss 1 week. Basically, won't be able to hand in your hand up. Okay. Yeah. Oh. So you can miss 1 week. You won't be able to deliver your handout that week, but you can present your work afterwards still. Okay, if that explains it.
I'll come to you in a second. There was someone from, yeah. No, every lecture, every exercise has 3. Every exercise has 3, and it's clearly defined what gets 1 point, 2 points, 3 points. So you attend 10 of them. So if you get 3 out of 10, so you have 30. Ataberk probably has some statistics distribution. There's also the question, if you're repeating, can you keep your grade from last year? You already attended the exercises. You can also do that. So there's a number of little details. We are trying to make it so that it works to your advantage as much as possible. The exercise this year and last year are identical, right? So you won't be doing something different this year. Obviously, working on it is good. I think another question to both of you is, the sessions are, these sessions, there will be assistants helping you out, but you have the board. You can come into the same labs, right? They can actually run those anytime they want.
I did not understand your question.
Ataberk, can they do the exercises outside the lab hours?
Of course.
So they can come here with their board to those rooms?
Well, if the rooms are available, yes.
Yeah. Sorry, there was, sorry, yeah.
Do we get, can we choose in which group exercises we want to go? Because I know I can't go on the team space or on the courses one.
Yeah, this should be cleared up with the Moodle post later on, if you can wait for that. Yeah.
There's a whole lecture on exercises and organization coming up. Someone from the middle was asking a question. Did I lose? No? Someone? No, no one. Yeah, sorry.
Not the person that wanted to ask a question before, but I do have a question. You said before on this sheet of things we will be looking at and things we will be skipping over. We're skipping over driver development, kernel development, and stuff like that. If you're interested in that, are there any resources to learning a little bit about that? Because that's exactly what I was wanted to do.
That's actually, so the question is, are there any resources available for driver development and things? So just to, let's say, glue the story together, if you're making a processor, that processor needs to somehow communicate to the outside world. And those outside world things are peripherals, devices that attach to a computer, and the operating system that manages your programs somehow needs to be able to talk to them. I mean, if you are a printer driver, you have to sort of say, yeah, give me some text, I'll make sure it appears and jams at the right moment and things like that. So there is some specific development for that. So this is a driver development. I'll be honest, I'm not from computer science. I don't know the exact curriculum, but that's a very, very important thing. If you're interested in it, you'll be very much in demand. I know that device driver writers, developers are sought after in a lot of places, and there will be things not in this lecture, and I'm not so aware of the curriculum to answer you. I'm very sorry. User's friend. Okay, more questions. I love questions. Questions are great. Oh, there's one question. Sorry. Just speak up. I don't. Oh, there you are. Yeah, it's not even a small guy. Yeah. Ataberk will talk about it. He has like 1 hour extravaganza about groups, lectures, exercises. Yes. Sorry. I'm looking at Mohammad because I'm not having any extra homeworks. Mohammad, it's your turn. He's the homework guy if there is one.
Yeah, we may have some extra credit assignment, but it depends on the lectures. We will decide later. Yeah.
Sorry, not the homework guy.
So to give you some context, like the last, version of this course, like last year, we had 4 extra assignments, and each of them contributes 1% to your final grade. So if you do, for example, 4 extra assignments, you can get 4% extra credit. That can help you to to get better grade. But we haven't decided for this semester, so we will see. Thank you.
I can explain the situation. The Safari group is in charge of the support. I'm just giving the lecture. So if I give an extra homework, I'm charging the Safari group to correct it. Right? That would be incredibly evil of me. Okay? So that's why I'm leaving that decision to them. Very honest answer. Oh, we are on YouTube. Nobody's watching anyway. Okay. If you have no more questions, let's take a break. Let's continue at the regular hour. If you have any other questions, feel free to come forward, ask them. Otherwise, Ataberk will talk about the exercise in the second hour.
jetzt schauen wir uns
Ich bin am Markt, aber gleich. Ich kann nicht mal überall nicht mal Wasser. Ich glaube, die beiden das ist schon ja, mittlerweile. Ich glaube, die erste direkt auf die Wasser am Kupfer kriegt. Nein, hast du nicht. Es gibt ja immer so viel Spaß hier. Ja, weil ich erzähle gerade mal mein Lebensmittel. Ja, das ist lustig. Ja. Muss die Leute richtig erzählen. Doch, aber ich mein erstes Mal gesehen habe. Aber du siehst nicht aus. Ja, gut, aber. Ja, ich habe jetzt nein, zu Hause. Mein Mitbewohner. Toll, nett, gut. Gut. Ja, stimmt, aber ich habe halt trotzdem obligatorische, weil ich studiere. Ja, es ist eine Regelung. Ja, ich brauche das Geld in Bar, das kann ich nicht machen. Ja, ich sage so, okay, aber wenn ich sterbe, dann die Geld geben. Ich sage wirklich so, das am Stunden. Stell mal vor, ja, er sagt 600. Aber ich das Geld nicht geben kann. Bro, ja, wir haben bei der Hotmachine. Die haben dann das ans Ärztetelefon gewiesen. Und dann kam er auch. Ja, aber so, ich habe das dann gegeben auf einmal, habe ich mal euer Vater später war nicht nach meiner Adresse. Die habe ich noch geschickt. Jetzt frage ich nach Identitätsdaten. So, soll ich mir auch noch Picknick schicken oder was? Also Bro, ich weiß nicht, wir haben 1 zu 4 entwickelt, danach haben wir uns an die offizielle Hotline vergeben. Also, dann kam der einfach. Keine Ahnung, was ich noch aber nicht mal. Aber nicht mal eigentlich
Ataberg, we have to start. Is it? All right. Hello? 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 Can you hear me? Hello, hello? Yes, hello? No. Hello. All right. Hello. Can we get started? Can anyone hear me? Hello, hello. Oh, okay. Let's get started. Come on. What? This is fine. Okay. Yeah, it's working, right? I can hear myself.
Okay, everyone. Let's get started.
Yes. All right. Hello, everyone. Welcome to DDCA this semester. And today I will introduce you to the labs those are the exercises Frank talked about in the earlier lecture, and to field programmable gate arrays. My name is Ataberg. I'm a PhD student in Safari Research Group, and my research involves designing digital circuits and prototyping them on FPGAs. So I'll start with some logistics immediately so that some questions you might have are cleared up. The labs will be on site in these rooms that you see in this table. Of course, it's not this simple. We will have some supplementary material presentations this semester in different rooms. Those are the rooms that I highlighted using color green here. So for example, on Tuesday, you will go to ML building E12 first. All of you will be there. The room is large enough. And then after 15, 20 minutes of introduction to that lab that you will do that day, you will move to the lab rooms that you see on the table above. You don't need to take notes of this. You will have these slides available on the website. And this table also is there on the website as a table on its own. So you can just go to our safari.ch/DDCA website and see where these rooms are and where you need to go every day. You will work in groups of 2. There will be 2 options to declare those groups. Either you declare your own or you will be randomly assigned by us. Of course, so let me make this point. If you're not compatible with your randomly assigned lab partner, let us know, and we will redo the assignments. Every group will receive an FPGA board, as Frank mentioned in the earlier lecture.
will have an in-class evaluation component for these labs, where you will receive the handout. You will work with your partner in the labs. You will get the tasks done that are stated in the manuals. And that will get you 70% for that lab's 3-point contribution to the total grade. So if you just do the labs, do the handouts with your partner, show your work to the TAs, per lab you will get 2.1 points, 2.1 points contributing to your total course grade. And 30% of that 3 points will come from the reports. So these reports are going to be about the labs. You will fill out these reports with your partner again, but you will have a more relaxed deadline for these. We expect you to deliver these reports 2 weeks after the lab they are distributed. And for the handouts, you will have 1 week to work with your partner to show your work in the following labs. Is that clear? Any questions? Yes. Lab reports should be English. Yeah, but does anyone have a better idea on that? I think we always had the reports in English, so that's why. That's my answer. Go ahead. I cannot hear you. Can you speak up a bit? Just one partner assignments. If so, the question is, will we change lab partners throughout the semester? Not if you want to. Okay. Yeah, so for the late submission of those reports, we have a 1-point penalty. And you should finish. This is something I already said. You can use your grades from, is that a question? No, okay. There are too many hands. Sorry, I'm a bit distracted when I look for questions. You can use your grades from past years. You can find your grades in past year's model. We will, yes.
I was just wondering with the lab reports, I reckon once we get to the labs, it will be further explained what the lab reports entail.
Exactly, yes. So the lab reports will be distributed in the labs. With the lab material, let's say. Yes, you can find your previous semester grades here at this link, and we will have, again, another Moodle post for you to select if you want to use your grades from past years, whether you want to do the labs this semester, and so on. For questions, Frank already mentioned this mailing list, but please send your emails to this mailing list so that all TAs receive them, so that we can answer them. All of us could answer them if some people are occupied with something else. We will have Moodle forums per lab where you can go and ask questions about that lab, and you can use Moodle forums for discussion. So what do we expect you to learn through these lab exercises? I'll try to cover those a bit, unless you have any questions about logistics. Any more questions? No, okay. So this is another view of the transformation hierarchy that Frank presented earlier in his slides also. You start with a problem. You try to develop an algorithm that solves that problem, essentially. And then you convert it into your programs. Then the operating systems, then the system software works that program on the microarchitecture using that hardware-software interface, and so on and so forth. You dive down. All of this just to tell electrons to solve some problem. Now we will look at these 3 layers in the labs. So you'll understand how a processor works underneath the software layer, and touch on implementation details at these 3 layers, and you will gain hands-on experience in digital circuit design and implementation. In the end, you will hopefully have learned how to make trade-offs between performance and area complexity of your digital circuit designs. And you will do this by gaining hands-on experience on prototyping using field programmable gate arrays. We will describe them, what they are. You will understand what they are a bit more in the upcoming slides. You will learn how to debug your hardware implementations. You will learn how to use hardware description languages, what hardware design flow looks like, and some certain computer-aided design tools that help us develop these digital circuit designs in FPGAs. So let's continue with a brief introduction to FPGAs. We will remain at a very high level, obviously. FPGA is short for Field Programmable Gate Array. They usually look like this. This is an FPGA. This is an integrated circuit or a chip of an FPGA. And these chips are often embedded in what we call FPGA boards so that they can be used for various applications. So what makes an FPGA so versatile so that it can be used in so many applications? Basically, it has reconfigurable simple functions, and you can reconfigure how these functions interact with each other. And then you can configure the input and output, physical input-output pins of the FPGA so that you can interface your functions, digital functions, with the real world. So let's look at how FPGAs compare against other types of integrated circuits, just to get an idea. These other types of integrated circuits that I show you here will be CPUs. That's the Apple M1 processor from the previous slides. Graphics processing units, which we might cover in the lecture later on. And what we call application-specific integrated circuits. Now, if you were to put FPGAs in this diagram, they would reside here. If you were to draw this flexibility to efficiency, to like an arrow from flexibility to efficiency scale. The more you go left, again, at a high level, the more flexible your integrated circuit is. It's easier to program it to make it work for the application you want. The more right you go, the more efficient it gets in performing a certain task. So FPGAs are more easy to program than, let's say, ASICs, but they are a bit less efficient than ASICs, and let's leave it at that. And this ASIC example, picture that I show you here is from Frank's lab. This, I think, is a chip developed for biomedical applications. And if you're interested in chips like these, please visit his website. What's wrong? Ah, that's bad. If Onur were here, Professor Mutlu were here, he will describe how unreliable computers are today. And this is one example. We cannot get this computer to share the slides with the Zoom session. I think it's good. It was good. Now it's not.
No, looks good.
So it's fine. Cool. Okay, we will continue after another short break. So, where are FPGAs used in today's? Where are FPGAs used today, except for getting points for the DCA labs? Now, this is one example. It's Microsoft's project Brainwave, where the researchers or engineers used these FPGA boards to accelerate some deep learning tasks. Another example is Amazon's EC2 F1 instances. These are cloud-hosted FPGA boards, where maybe as a customer, if you don't want to purchase a lot of FPGAs, but you have tasks to accelerate using FPGAs, you can hire, not hire, but rent Amazon's cloud service and perform your tasks in their cloud infrastructure. FPGAs are used to accelerate DNA sequencing tasks. There's more use for them in genome sequencing, and these are example work that we have done in our group in the past. This is the first alignment filter that was accelerated using an FPGA board. And we published this work on bioinformatics in 2017. It's a prominent, I will say journal, but correct me if it's a conference in the field of bioinformatics. And you can find more insights into how FPGAs accelerate genome sequencing in this paper if you're interested. So I'll skim through these. I'll flash you some work that show where FPGAs are useful for. Now, there are other steps in the genomics analysis pipeline that you can use FPGAs to accelerate. In this case, it's base calling, and the researchers here show that you can accelerate base calling by around 16 times compared to the state-of-the-art base caller using an FPGA platform. And you can find more details about that here if you're interested. It's not only about genomics, fortunately. We can accelerate climate modeling tasks using FPGA platforms. And in particular, this work that researchers from our group in the past did, it showed that FPGA-based near memory computing can accelerate some certain tasks. In particular, they showed for these tasks, they accelerate. They have performance improvements ranging from 5 times to 27 times compared to a regular computer, 16-core computer. We also use FPGAs to test memories in our group. This is one platform we have developed, FPGA-based platform that we use to test real DRAM chips. And it allows us to gain understanding into the problems, for example, reliability problems of these chips, or uncover new functionality in real devices that are otherwise not revealed by standards or specifications that come with them when you purchase them, for example. This platform is open sourced on GitHub. You can find more information about it at this link. And a newer version of it called DRAM Bender that we use to test more modern DRAM chips. And a description of that platform, a paper about it on arXiv. And this is how it looks now, the newer version of the platform that we use to test DRAM chips. In the past, an even earlier version of this platform was used to uncover the RowHammer vulnerability in many chips in the field. RowHammer is a prominent vulnerability, reliability problem in DRAM chips, basically. And we have gained more understanding about this problem over time using newer versions of our platform. And at some point, DRAM manufacturers themselves tried to fix this problem in their DRAM chips. And we used our platform to recover information about those fixes they have, for example. And you can find the artifacts of this work in this link. More insight into RowHammer using our platform. And recently we found a different source of vulnerability in a newer DRAM chips called RowPress. The other use of these FPGA-based testing infrastructures for DRAM that allows us to uncover new functionality. In this paper, we found that you can activate simultaneously not one, that's the default behavior, but 4 DRAM rows, and you can use that to generate random numbers, true random numbers at very high throughput. Again, the artifacts are available on GitHub. And we don't use these platforms to only test DRAM, main memory based on DRAM, but also flash chips, for example, other types of memories, and we understand them even more. We use FPGAs to prototype different types of systems. So we have a research idea, we can, in theory, or we can practically port it to an FPGA board. We can make it work in an FPGA board and evaluate it there. And that kind of shows you how your idea would look like if it was implemented in a real system. An example of that is this work. And another example of that is another work that's called Metasys. It's a similar use for the FPGA boards that we have. And this got a Best Paper Award recently at HighPeak conference in Europe. And its artifacts are also available on GitHub. Okay, so we'll switch gears a bit now. We'll go talk about lab exercises again at a very high level. I'll try to introduce them one by one. But keep in mind that the introductory material presentations will give you more details about these labs than what I give you here. This is our FPGA board. It's a Buses 3 FPGA board. It has many inputs and outputs that I highlight here. And you will learn how to use all of these, well, not all of these, but most of these throughout the labs. Let's move on with a high-level summary of the labs. So as Frank mentioned, at the end of these exercises, you will have built a 32-bit microprocessor running on the FPGA board. And it will be able to run pretty much any program you can develop. Each week, we will have a new exercise. Not all the exercises will require an FPGA board. I'll talk about them. And you're encouraged to work with your FPGA board, experiment with the board on your own. Now, to keep this presentation a bit less boring, I had prepared a joke, but then Frank stole it. You cannot destroy the board by programming it. You can destroy it by other means. Now, it's not funny anymore because Frank did it. Anyways, okay, let's move on. Lab 1, you will draw a basic circuit. You know about comparison. You have probably used it in your previous courses to learn the relation between two variables. So you will, in this lab, have two electrical signals. You will compare them and output an electrical signal based on the result of the comparison. You won't need an FPGA for this. You will do the drawings on paper and show your work to the TAs. But we encourage you to try it later. In the second lab, you will work with FPGAs. What's another common operation in software programming? It's addition. So you will design a circuit that adds two 1-bit numbers. And then you will learn about the modularity aspect of digital design. So you will reuse this 1-bit adder to construct a 4-bit adder. And then you will interface this adder, 4-bit adder, with the real world using the inputs, the switches as inputs to your FPGA design and the LEDs as the outputs. In the third lab, you will show the results of your adder circuit in a more human readable way using the 7-segment displays. And in lab 4, we will you will switch gears this time a bit. So you will apply sequential circuits for the first time. All labs until this point will be about combinational circuits. Now you will work with sequential circuits. That means you will learn and use memories. And you will design something that simulates the turning signals for a car. And you will change the blinking speed to spice it up. You will implement an ALU in lab 5. This will be your first step toward designing your processor. Why? Because, sorry, let me explain what the ALU stands for arithmetic and logic units, and that's somehow self-explanatory. So this means this unit is able to do some arithmetic operations and logic operations. Arithmetic operations being addition, subtraction, multiplication, and logic operations are like logic and OR operations. You will learn about these more in the upcoming lectures. So it's fine if you don't understand everything at every level of detail. In lab 6, you will learn how to methodically test these digital circuits that you have developed. You will simulate your design and you will learn how to debug and solve some problems with your design. In lab 7, this will be a bit of a different lab because you will be writing assembly code. You won't write Verilog code. You won't design digital circuits in lab 7. These boxes show you two examples for the same code. You can see the assembly equivalent of a high-level C code over there. And you will implement a program that you will later use, that you will later run on your processor that you develop. And this will be an image manipulation program. In lab 8, we will dive into full system integration. This means you will be designing your processor in just 2 weeks. You will learn how a processor is built. And you will complete your first design of a MIPS processor. MIPS is an instruction set architecture that we will later describe in the course. You will run a snake program on this processor that will generate this pattern on the 7-segment display. And in lab 9, you will improve the performance of your processor by adding new instructions to it. 2 examples we give here are like multiplication and bit shifting. These operations will help you improve the design of your process, improve the performance of your process. We will have, again, let me repeat these supplementary material presentations. I've touched on the highest level details about what you will do in the labs. These presentations, it's important for you to attend these because we will introduce you to the labs and you will have a better idea on what to do in the lab if you actually be present in this supplementary material presentations. Okay, do you have any questions about the labs? No questions. Cool. So I'll try to explain field programmable gate arrays in a bit more detail to you, but again, we will remain at a very high level. Don't worry. So recall that FPGA is a reconfigurable substrate. It's a versatile substrate that we use for many tasks. And remember that it sits in this position, in that position, in the flexibility to efficiency scale. This is a high-level block diagram of an FPGA. So you have logic blocks, switch blocks, interconnects, many blocks. And the key idea here is that all of these are reconfigurable. So you have hardware that you can reconfigure for a certain task. It's made up of two main building blocks. One of the building blocks is called lookup tables. The other one is called switches or switch. And this is a lower level picture of what an FPGA looks like. So it might be a bit overwhelming. Focus on the elaborated view of the lookup table here. It's made up of more blocks. It has what we call a multiplexer that you will learn later in the course, and what we call a configuration memory or data inputs, and some flip-flops as for us to use as memory elements. This diagram on the bottom right shows you the fraction of the area that one component occupies essentially in the chip. And the key from this block, the key from this diagram is your interconnect actually takes up most of the area. The reconfigurability takes up a lot of area. So that's, again, tying to the trade-offs that we had. ASICs are better more efficient at doing one task partially because FPGAs require a lot of area just to have reconfigurability, support for reconfigurability. Okay, so we move on and we discuss what a lookup table looks like. So this slide, we will focus just on how it's organized. There are many blocks. What are these? A multiplexer takes a 3-bit input and outputs a single bit in this example. And you remember bits. Bits are binary digits. It's either a 1 or a 0. So here, yeah, again, as I said, multiplexers chooses one of the 8 data inputs, 8 yellow blocks that corresponds to the 3-bit select input. And these are the data inputs, and this is your select input. The select input, as I show you here, essentially addresses these data inputs, right? The way you see here. If the input is 1, 1, 1, we will select, the multiplexer will select whatever is written here. This is going to be a 1-bit digit, one binary digit, and we'll output that, whatever is written here. We will see an example that explains this better. So I'll make this claim that a 3-LUT, this is a 3-bit input lookup table, can implement any 3-bit input function. And I'll leave this to you as an exercise to figure out with the information that you will learn later on in the lectures. But we will see an example, and maybe you will have an idea on why this is the case. So let's implement a function that outputs a 1 when there are at least 2 1s in a 3-bit input. In C, you could write this program, and that will return you the correct value to this function. Or you could write it like this. It's a switch case version of the program above. You're basically enumerating all possible input-output combinations. If the input bits are all, if there's 1, 1, that's if the value is 1, there's 1, 1. If the value is 2, there's still 1, 1. So basically, you're writing the truth table for that Boolean function, and you're initializing the data inputs for the lookup table based on that truth table. So let's fill these data inputs out. If the input has no 1s, it will output 0. If the input has only 1 set bit or 1, it will output a 0. Still 1, 1, right? This is a bit confusing when you keep saying 1, 1. Until you come to this case where you have 2 1s in the input bits. So you will output a 1. And then again a 0, and then all 1s, because there are more than 2 set 1s, at least 2 set 1s. And then once, so what happens here? If the input is 0, 1, 1, for example, you will select, can you see the cursor? Yes. You will select this value, and you will output that. And that will correspond to the output of the function you were trying to implement. So you enumerate all the input-output combinations and put the values in the data input. Okay, we have a 3-bit input function, but how can we implement a microprocessor? It's certainly not a 3-bit function, right? Well, FPGAs are composed of many of these lookup tables and switches. So this is only a fraction of what you have in a chip. And Modern FPGAs have more than just 3-bit input lookup tables. They have 6-bit input lookup tables and thousands of these, and a lot of memory, and even hard-coded special purpose hardware blocks for high-performance operations where your FPGA logic cannot meet the demands of. These are memory interfaces or other low latency and high bandwidth input-output interfaces. And sometimes you will even have a general purpose processor built in the FPGA chip. So this is one example from, this is a relatively new platform from Xilinx. You have in the programmable logic side, this is the FPGA that we discussed so far, the yellow highlighted part. Even in the programmable logic, you can see that you have some specialized circuits like for storage and signal processing. And the outputs of these and the inputs of these specialized circuits are reconfigurable also. And on the other side, you have the processing system in the same chip that has a whole processor implemented next to your FPGA. So this is how you can implement more complex functions using FPGAs. Let's summarize the advantages and disadvantages of FPGAs in context of this diagram. So first, you can implement an algorithm directly in the hardware. This gives you high specialization, and you can have high performance and energy efficiency compared to, for example, CPUs. It has a lower development cost compared to a custom hardware design because you can write Verilog code and implement that in the hardware. Whereas for hardware design, for specialized circuits, you have to go through many more complex stages like fabrication, one example. You don't have to fabricate this chip again and again if you want to change the design of it. It has shorter time to market versus a custom hardware design, and it is reconfigurable in the field. And because it's reconfigurable in the field, for example, you can patch a hardware circuit. Right? That's a thing with FPGAs. And because it's reconfigurable in the field, it's usable and reusable for many purposes. So one day you can use the FPGA board for prototyping some design, and in the other day you can use it for to get some points for DDCA labs. And the disadvantages are they're not as fast and power efficient as dedicated hardware customized for an algorithm. That's the ASIC. Because reconfigurability comes at a cost of area and latency overheads. So we talk about FPGAs being programmable, but how do we program them? We use what's called computer-aided design tools because FPGAs have many of these resources, many of these lookup tables. Imagine filling all the data inputs one by one with your hand. It's impossible. They're hard to program manually. So how can we represent a high-level functional description of our hardware circuits using the FPGA resources, in terms of FPGA resources? These questions will be answered by computer-aided design tools, basically. Select the resources to map our circuits to. These resources are the lookup tables and all the switches. And optimally reconfigure the interconnect between the selected resources and generate a final configuration file that the FPGA is able to understand and configure itself with. So this is an example of the FPGA design flow. We will start with a problem definition. This is representing the tasks in your lab, basically. Problem definition, we start with that. We use a hardware description language to solve this problem, to describe a solution to this problem using digital circuits. There are many different hardware description languages, such as Verilog and VHDL, and many others that I don't show you here, but we will use Verilog in these labs. And this will be your task in the labs. Now, there are other steps like logic synthesis, placement and routing, and bitstream generation that will be handled, automated by Xilinx Vivado tools that are already installed in the labs. And finally, you will download this generated bitstream onto an FPGA chip. I just have one slide about Vivado, just some logistics, right? This is a software tool that helps us with FPGA design flow. It looks something like this. When you open it in the labs, you will see some window like this. It provides some tools to simulate our designs so that we can validate the correctness of our implementation. And for debugging, it will provide drivers. Well, this is not so much relevant unless you're installing it on your device yourself, but provides drivers and graphical interface to easily program the FPGA board with the bitstream that you developed. It's already installed in the lab computers, so you don't need to install them on your laptops if you can go there. In these slides, I have a tutorial and a demo for using this Vivado tool to develop a circuit basically and make it work in the FPGA. But I won't show you the full tutorial. I will leave you to go over the tutorial on your own time. This tutorial will allow you to follow the FPGA design flow steps and download the bitstream into the FPGA. It's a simple keyboard demo that you will be able to easily develop at the end of the semester with the knowledge you acquire. And these are the link to the source files for that demo. And so there's a short video where we go through the demo. You can watch this on your own pace. So I won't show this here. And with that, I am done. Just 3 reminders. You don't need to install Vivado on your laptops, but we have on our website a tutorial for you if you want to do that very badly. Okay. Do not ask TAs to grade your labs outside of lab hours. The grading for the lab handouts will be done in the labs. Please don't force TAs to grade labs outside lab hours. They have a life also. And submit your lab files in the correct format. So these formats are specified in the lab reports and the handouts. Please abide by them. And this semester, we won't grade basically incorrectly submitted reports. We'll give them 0 points. And always double check your grades. This means when you get graded by your TA in the labs for a handout, double check that you have indeed been graded on Moodle. Go to Moodle, go to that lab, check your grade. Okay? Any questions? All right, keep following Moodle. No, okay. Okay, keep following Moodle for announcements about the lab selection, group selection. Thank you.